Hi guys, I'm back. I know you can't see me very well because it's night. There's not enough light in here. Anyway, I'm going to switch to the slideshow, but I'm back to talk about nuclear energy. So again, this is chapter 13 content in our environmental science textbook. So let's get the screen up here. Oh wait, I don't want to share this part of my screen. I want to share this part of my screen. Okay, so slideshow from the beginning. All right, so we're talking about energy and then in particular power, right? And the amount of energy that is delivered over a specific amount of time to a home, to a factory. And of course, the different materials that we use to create power are different kinds of natural resources, and they all have benefits and they all have less desirable things about them. But kind of on balance, we are learning as a society that fossil fuels have particularly high kind of externalized costs. And so we're interested in moving away from using fossil fuels to create our energy and to create our power. And so we want to think about what other options are. So first we'll talk about nuclear power. Okay, so basically how does it work? Well, the idea is that we have certain kinds of isotopes, which we've mentioned earlier on in the class, right? These are versions of a particular atom of an element that have typically extra neutrons in their nucleus that make them a little bit heavier than average, or at least different weight than average. And that extra weight that is typical of an isotope causes, in some cases, for them to be particularly unstable. And these really unstable isotopes that will actually break down, the nucleus of the element itself will actually break down and spew out different matter from the nucleus and lots of energy from the nucleus. Those particular isotopes are radioactive isotopes. So not all isotopes are radioactive. But certain isotopes like uranium-235 are radioactive. And this process is called decay. And radioactive decay occurs, and as it occurs, often the end in a kind of chain of kind of spewing material of an atom would result in that element actually transforming into a new element. And so in many cases, it's easy for us to understand how this decay reaction is proceeding because we start out with one thing and we end up with a completely different thing. And we can kind of, in nature, let this decay process happen kind of without human influence. It's going on all around us all the time, but usually in most places in very low kind of concentrations. However, if we bombard certain radioactive isotopes like uranium-235 with neutrons, right, these materials that don't have a charge would have a little bit of weight that can be found in the interior of an atom, we can create what's called nuclear fission, where we can break up some of the material in the nucleus of the atom. And we can set off a high energy chain reaction. So it's not just like one reaction or one change happens as materials released from the nucleus. Often there's kind of a series of steps over which different materials are being released. But if we do this in a particular environment, in a reactor core, which is what we'd have in a nuclear power plant, then we have an enormous amount of energy that's released as part of this kind of nuclear fission or nuclear breakdown process. So this is what they're doing in nuclear power plants. They're usually also controlling the rate of the reaction, trying to slow it down a little bit by, one, controlling the rate at which they're bombarding different radioactive materials with neutrons, but then they can also kind of slow this process down a little bit by trying to cool the environment, usually with water. And then beyond that, the process works in the same way that we discussed it would work if we were burning coal. Basically, the energy that's produced is used to boil water. Water creates steam. Steam rises and turns turbines and turns generators that use magnets that move around rapidly. Metal that creates kind of electrical charges, and then that energy can be moved along different kinds of electrically conductive material like wires, electrical wires, into eventually people's homes. So that is kind of the end game for nuclear energy. Of course, we have used this technology to release enormous amounts of energy all at the same time, like in bombs, which has been pretty devastating. But primarily, the use for nuclear energy is for electricity production. So just like coal, that's its main use. Okay, so nuclear power is used in different places around the world. It is primarily concentrated in areas that are wealthier and have a little bit more scientific and technological kind of prowess. And so places like the United States, places like Europe, places like East Asia have used nuclear power much more than parts of the developing world. In the US, we have 104 nuclear reactors, which is almost 25% of the total number of nuclear reactors on the planet. We produce about 8% of our energy through this type of electricity production. And then, as I already mentioned, places like countries in the EU and places in like Japan have a particularly high dependence on nuclear fuel. One other comment I have on the slide, which is worth mentioning, is a lot of our nuclear reactors were built many decades ago and they're aging. And so we kind of are at kind of a critical point here where we really need to make some investment in upkeep to make sure that these are safe. Or if we're deciding that we don't want to continue on the route with nuclear energy, then we need to be kind of shutting these down. Okay, so the benefits of nuclear energy are many. So one is that they're extremely energy efficient. They produce a lot of energy in a small amount of area. So I'm going to move to the next slide and then come right back, but just to kind of emphasize that point. So this graph shows different materials in the left column, and then energy density in the middle column. So megajoules, 1,000,000 joules of energy produced per kilogram of material combusted or utilized. So how many million joules can we produce per kilogram? Would be about 10. Ethanol, which is a fuel often created from like a biofuel from corn that we can use as like a liquid gas for transportation, would be about 26. Coal would be about 32. Crude oil, close to 42. Diesel, close to 46. Uranium, let's see, 570,000 natural uranium, and then reactor grade uranium would be 3.7 million. So how long could 1 kilogram of each of these materials create energy to keep a 100 watt light bulb on in your home? Well, a kilogram, about 2 pounds of wood, could burn a light bulb for 1.2 days, ethanol 3.1 days, coal 3.8 days, crude 4.8 days, diesel a little over 5 days, natural uranium 182 years, reactor grade uranium over 1,000 years. So this is kind of orders of magnitude more energy dense compared to the other kinds of fuels that we're talking about. So in terms of energy efficiency, this is a really effective way at producing a lot of energy quickly and in a small space without having to need access to a lot of material to create that energy. Okay, and then of course, if we are using this kind of energy production, then we are going to be able to move off fossil fuels, and we've talked about all the different kinds of costs associated with fossil fuels, so that is a plus. And then the energy production phase of this, at least, probably some of the mining is a little bit different, but the energy production phase does not release any greenhouse gases. So as we're breaking down uranium-235, it's not releasing methane, it's not releasing carbon, and it's not releasing, or carbon dioxide, it's not releasing NOx and CO2 and these other things that we know are creating big shifts and somewhat problematic shifts in our environment. So now there's also some less desirable consequences of being dependent on nuclear fuel. First of all, aging equipment. So 50% of the nuclear power plants in the United States are over 30 years old, and they're approaching the end of their expected lifespan. So at the time that these were constructed, they kind of had a plan that said, you know, they were expected to run efficiently for this long. So we mentioned before, now is kind of a critical point to think about, are we going to be revamping these, building new ones, or moving away from this type of energy source? Then a big one are the risk associated with different kinds of accidents that might happen. So we have some pretty infamous accidents, places like Chernobyl, and then the kind of Fukushima power plant breakdown that happened during the big tsunami in Japan back in, let's see, I think that was 2011. And when this happens, even if they do have extensive safety plans in place, sometimes some sort of natural disaster is kind of really out of the scale of the kind of thing that we've prepared for. And we can start to leak radioactive materials into the environment. And as you're probably aware, radioactive materials are not good for people. It's not good for us to be exposed to this material up close. And it gives us really high increased risk for certain kinds of diseases, particularly certain kinds of cancers. So we want to be really safe with the way that we're handling radioactive material. And if all of a sudden we lose control of that radioactive material and it spreads in their environment, we have a lot of potential public health concern around that. So that's probably the main concern that a lot of people have. Then third, of course, we have to mine this material. This isn't something that's just, you know, shining down on us every day from the sun or blowing past us every day as the wind is. So we have to go out to places where this exists. We have to mine and transport this material. And so there's health impacts related to the people that are working in these mines and the regional areas where this mining is taking place. And of course, we use fossil fuels to do all this mining and do all this transportation of fuel. So there's some kind of negative costs there. And then kind of a final and also a pretty major consideration is nuclear waste. So we use these different kinds of materials that have really high concentrations of, like, often or most typically uranium-235 in them. And we use them for a period of time, but then at some point we are kind of done using them. They've given us the energy content that they contain, but at that point they are not kind of efficient to use in a power plant context, but they're still radioactive and they still will be radioactive for a long time. This radioactive decay process can take, depending on the material, thousands to millions or even billions of years. And so as we continue to produce electricity and energy through this concentrated radioactive material, we continue to accumulate a lot of this waste, and then we have a problem of, like, what do we do with it? Where is a safe place to store it? How is a safe process that we can use to store it? Where would that would be equitable and safe for people. And so most people feel like they don't want nuclear waste stored in their backyard. And I don't want nuclear waste stored in my backyard. So I am definitely sympathetic to this. Even though, as we discussed, there are a lot of potential benefits related to the kind of energy efficiency that this particular type of resource could promise us. Okay, so as I already mentioned, once these reactors have lost productivity, they're still radioactive. Usually they contain not anymore uranium-235, but instead uranium-234. So they've kind of decayed to that stage. Also neptunium-237, plutonium, cesium, and other forms of radioactive materials. This kind of high energy that continues to be released from these radioactive materials can harm our living cells, cause cancer. We already mentioned this. And the radioactive materials will contain potency until all or most of the unstable isotopes have decayed. So they must be isolated for the environment for a really long time. And as I mentioned before, a really long time is not like 50 years in most cases. It's like tens of thousands or millions of years. So the idea with radioactive materials is that we can't time exactly how long it takes for each kind of radioactive atom to experience this transformation or decay. But if we have a large group of atoms, we can estimate how long it will take for half of them to break down, and that's what a half-life is. So if we have a bunch of uranium-234 byproduct, kind of a waste product from the reactor cores of a nuclear power plant, and we want to store them in a safe place, after 236,000 years, they're still going to have half of the radioactive material that they did at the time that we started to store them. So we're talking a long time, a really very, very long-term investment in storing this nuclear waste. Okay, so I sometimes have had questions from students about like, well, what is this nuclear waste? What does it look like? And so there are actually different grades of nuclear waste. So first of all, there's the spent reactors, and these reactor cores are like long, solid rods of kind of like basically like a metal material that contains some of this really highly radioactive material. And so one of the things that they do to store these materials once they're done is they put them in these what are called dry casks. So I have some kind of images down here with some information that shows kind of a person and then how long these reactive cores are and then how long these dry casks would be that they would be stored in. So that's what that would look like. But then there's lots of other material that's also considered radioactive waste, which is other material at the power plant that has kind of come in contact with that radioactive reactor core, because that material may contain some of this radioactive content as well. So like water that was used as a coolant, and this is what happened in the Fukushima breakdown, all the water that was kind of flooding this power plant to try to cool down the reactor core and get it to turn off. And then there was like ocean water coming in, and then all this kind of now radioactive water was kind of released into the ocean essentially. And then we kind of lost control of it. Anyway, all that water that would have been circulating around in this environment, we also need to store for a period of time and keep away from people. And the solution that we have for these materials at this point is that we have 8 facilities that are underground facilities where we store this material. And some people have suggested things like we should send it out to space or sink it down to the bottom of the ocean, or dig huge pits underground and store it forever. But regardless, a lot of people are uncomfortable with the idea of this material that could be harmful for a long time, and if we kind of depend on this a lot, and build up more and more and more of this material, then we're going to potentially kind of have a lot of this to deal with over time. Okay, so those are some of the considerations about nuclear energy.